Hello, welcome to my talk, NIM Metaprogramming in the Real World. I'm Andre Van Hoek. You can find me on GitHub as Treeform. Let's get into it. Why use metaprogramming? This is the question I want to answer with this talk, and I want to give you a real-world example from some of the libraries that I have written. Hopefully by the end of this talk you'll know why and how to use metaprogramming in NIM. First, I want to get across this idea of metaprogramming power levels. And the lowest end, we have generics, which sometimes isn't even considered metaprogramming, but it is a way to get interesting functionality. Then we have templates, which is basically like code substitution, like copy pasting code. And then finally, we have macros, which basically can do almost anything. But they're kind of hard to write, and they put you into the chair of a compiler writer. It is always a good idea to shoot for the most minimum metaprogramming power level you have. So if the problem at hand can be solved with generic, you should just use generics. If it requires templates, use templates. And if you need to use macros, use macros. But don't jump on macros right away when a simple problem can be solved in a simpler way. Let's look at some examples. Let's look at level 1, generics. Generics allow you to compose different types. In a type language, you almost can't do anything without generics. For example, we have a sequence. If sequence didn't have generics on it, it would be very cumbersome to use. For example, we have to create sequence of integers, sequence of strings, sequence of some other format, and that's like just a lot of sequences and a bunch of repetitive code. That's why generics exist, to get us out of this problem, right? Just create a sequence with a generic T, and then you can create sequences of a bunch of types, including sequence of integers, sequence of string, sequence of float. It's really easy to use then. In NIM, generics, I think, are really powerful, and you can use them for some very interesting results. Let's look at VMath. VMath is one of my libraries. It's a vector graphics math library for NIM that aims to follow GLSL shader naming conventions and be very fast. Why GLSL? There's a lot of documentation and examples on how to use GLSL shader languages, the accompanying vectors and accompanying matrices. VMath tries to just follow those conventions so that there's less surprises and less things to learn. You can find VMath on my GitHub at treeform/VMath. Here's how I use generics in VMath. I have a generic vector of size 3, and you can see it's an arbitrary type T, and then I have X, Y, and Z component be of that type. Using this generic vector, I can create more concrete vectors that you would expect from GLSL. For instance, the binary vector, bvec3, as well as an integer vector, ivec, as well as an unsigned integer vector, as well as a normal vector 3 that a lot of people use with GLSL, and then the d vector, the float64 version of the normal float vector. So yeah, using that generic gives me a lot of power. Here's an example. Length. Now I can just write a single length function, and that will work with any type of vector, with integer vectors and with float vectors, float32, float64, it doesn't matter. I write the function once. If the vectors weren't generics, I'll have to rewrite this function over and over and over again for each type. And while doing that, I'll probably make some mistakes, or it's just hard to look at and hard to reason about. So this is why I use generics. And all of the functions in VMath are some sort of generic version of the general vector or general matrix. Generics don't cost any performance. They get compiled in and are very fast. This makes VMath fast as well. Some other things we do is we have a bunch of benchmarking tests, and we profile the VMath library pretty often. If you find a faster vector math library for NIM, send me a message. Next library I want to talk about is Jsony. Jsony is a fast JSON library with hooks. The idea when writing this library is that you want to turn the JSON you have into the objects you want. The idea here is that In the wild, JSON can be in a variety of formats. And you also have objects that you like, that is structured the way you think. Jsony allows you to map those wild JSON into the objects that you want without an intermediate step by using hooks. You can find Jsony at treeform/Jsony on GitHub. Jsony has a very simple API. You define your object, say an account object with name, score, and account ID. And then you have some JSON, which basically has the same thing, account, name, and score. And then you just call from JSON on that string, and then you get the account back. If you want JSON back, you can just, on the account, call toJSON. It does some nice things. For instance, it does the name conversions for you. In JSON, it is very common to use snake case with the underscores, while in NIM, it's very common to use camel case with the capital letters. Jsony just translate those different naming conventions automatically. The other thing that Jsony does is if there's any values that are missing, they just get default values in NIM. Again, use the JSON you have, not some theoretically clean JSON. Interesting thing about Jsony is it's all written using generics with polymorphism. There's no macros, there is no templates. It's all generic, and it's all built using parse hooks. This makes it very, very extendable. Here's an example. It's very composable. Very often in JSON, you encode dates as strings. And here's an example of date being the string. With a parse hook, you can actually turn it into a real datetime object. You just do parse hook, you first parse it as a string, and then you just convert it automatically to a datetime. Now, wherever a date like this appears and wherever you need a datetime, Jsony will use this hook to auto-convert. It's very nice for this reason. Likewise, you can create a dump hook, which takes a datetime that you have in your object and converts it into JSON by first formatting it and then dumping it as a string. Again, if you have any datetimes in your objects, converting them to JSON, there's just two Jsony is very easy. And the cool thing is these dump hooks are very composable for any type you have, for almost any situations that you might run into. So this what makes Jsony powerful. And this also what makes NIM's generics pretty powerful as well. Again, generics are compile time code. They don't hurt performance like you would have in a dynamic languages or with dynamic dispatch. This keeps Jsony very fast. Other reasons why Jsony is fast is it does not need to create an intermediate JSON nodes. There's no step which just parses everything, creates a bunch of nodes, and then converts it to objects. No, Jsony converts the JSON as it's parsing it directly into the objects that you've supplied it. This saves a ton of memory allocations, and as we know, memory allocations are pretty slow. So that's why Jsony is fast. Let's look at another level, level 2, templates. Templates enable code substitution. They're pretty simple to understand. It's almost like copy-paste, but they can be used for very cool things. Let's look at them. Here's a great example for why I love using Jsony 4. So you have kind of like a little GLSL languages to create either UIs or HTML. Here I'm just giving a very toy example. So at first we have the rectangle body, and then we create a rectangle inside it called button, and then on a button we create an on-click handler called click, and that just echoes some text, hey, you clicked. Pretty simple. With the templates on the bottom, you can see I create a rectangle and it takes a name, well, ID in this case, and then it takes a body, which is untyped. Untyped is a special type reserved for templates. What it does, it basically takes whatever you pass there and will substitute the body inside the actual template. As the template starts, we have a push rectangle, which means we do some sort of initialization, and then once we're done, we'd pop a rectangle and do some desinitialization, who knows what else. The interesting thing is these templates, they nest really nicely. And then we have another template called the click handler. Again, it just takes a body, and that body goes inside the if statement. Just if mouse overlaps the current rectangle, you do something. And this is pretty cool. And this actually just turns into simple NIM code. We have a push rectangle, then we have another push rectangle, then we have the if statement, and then we have pop and another pop. Doing this in other languages might involve closures or callback handlers. None of that is needed in NIM. With templates, you can write pretty clean, pretty clear code with just a few lines. And I think templates are great for these kind of small DSL languages. DSL stands for domain-specific languages, languages that are only basically live inside your program and don't have to go outside. Let's look at VMath. Again, remember the VMath is one of my vector graphics math libraries that is very fast. It's very error-prone to write repetitive code, and this is where templates win. Well, they do copy-paste, after all. So here we have a bunch of procedures that we need to define for all the vector types I have. A bunch of additions, a bunch of reciprocation, multiplications, divisions. Like this will just go on, and I'll probably make a bunch of copy-paste errors. And when something needs to be changed, again, copy-paste errors, repetitive code, very hard to look at. You can fix that really easily with a very simple template. For example, here I have a very simple template that generates code called gen operator. What you do is you pass it an operator, and then it generates an operator for all the different vector types. And then all I have to do is just call gen operator on all the operators I have. It's a lot less typing, you'll make a lot less errors, but it is more complex. I don't recommend using templates to save a few lines. If you have a lot of lines to save, it's great, but they do introduce extra complexity, extra something you have to understand and debug. So I only recommend templates when you can actually save those lines of code, when it actually makes sense. Let's look at another cool library I made called Windy. Windy is a windowing library for NIM that uses OS native APIs to manage windows, as well as set up OpenGL context and receive input events, mouse, and keyboard. It's very similar to GLSL or SDL. You can find it on treeform/windy. The idea here is I wanted to fix a couple bugs in GLSL as I found, but it's a very big project and it's very hard to understand. Why? Because it's not written in NIM. GLSL and SDL both kind of have not exactly NIM APIs to them. I ended up writing almost like a layer on top of GLSL to be more NIM-like. And then I said, why do I have this layer when I can just go to the operating system directly and understand directly how operating system work? And I can get some other features which GLSL didn't want to support. For instance, IME for Chinese, Japanese, and Korean language input. Here's an example of using templates in Windy. You can see I'm using here to generate some Objective-C classes that are needed to talk to the Mac API. We use a low-level Objective-C interface from C. It takes a lot of code to generate these objects normally, but we have created a template that is very simple. Just add class, the class you want, the super class, and then whatever NIM class you want this to bind to. Same thing for methods. You do add methods, the string method in Objective-C. As you know, Objective-C method names are kind of strange. And then the NIM functions that we want to bind this to. We just create this object in NIM that looks almost exactly like an Objective-C class would look like. We just create a bunch of them and it saves a lot of code in Windy. This is how that template looks like. You can see it starts out with a template, add class, you pass it the 2 class names and then other things and the body that you're going to use. We call low-level Objective-C things like Objective-C allocate class pair and other methods that are needed to make this work. Then we actually have templates inside the template. The cool thing here is that add protocol and add method, they don't exist outside of add class. So if you try to use them outside, it will just not work. But inside the body, you can use them. And that's, another use case for a domain-specific language, kind of cool. Again, we have the methods to add the protocol, which Objective-C classes have, as well as add method, which, is another, class add method low-level Objective-C call that's kind of strange looking. But after that, we have the body. That's where we get all that other code comes in here. And then those add methods just get turned into these calls. And then in the very end, we register the class pair with the Objective-C runtime. Again, templates saved us a lot of repetitive code and it is just so much easier to use. Templates are awesome because the meta model they have is very simple. It's basically, if you can do copy paste, you can do templates. Yes, there's some weirdness and some typings you have to do, but otherwise templates I think are great. I highly recommend when you have a bunch of code to use templates. Again, remember the power levels. If you can solve your problem with just generics, do it. Don't go for templates. But if you can use templates to solve it, without going to macros, use templates. Finally, we are at level 3, macros. Macros makes you basically a compiler writer. They can do almost anything in them, as I'm going to show here. I want to introduce my library, Shady. Shady is a NIM to GLSL compiler. Again, you can find it on my GitHub, treeform/Shady. Shady allows you to write cool shaders like this one here. This is computed by a shader. It creates a very cool looking flare. Here's an example of the flare function. You can see it is just pure NIM code, maybe exception of that uniform over there for the time, but that just turns into normal float 32, no problem there. You can see almost all the code is pretty math heavy inside it. It is all using the VMath vectors and matrices. It's pretty cool, and it allows you to basically write shaders in NIM. There's something that you cannot do with this thing is to allocate memory. So using sequences or ref objects is basically not allowed in this model. So you have to find workarounds. This is how easy it is to use. We create that flare thing and we can easily test it by passing it a test color, a vector, and then a time, and then we get a test color back. We actually run that flare on the CPU. There were no shaders involved. It just runs. But you can also compile to a shader by calling to GLSL macro. And it just returns you the string representation of the function that you can pass to the rest of your system to initialize the shaders. GPU shaders are really cool, and bringing them to GPU shaders is also pretty awesome. But shaders are very hard to debug in their GLSL form, right? There's like no echo statement, and yeah, it's just hard. Writing my shaders in Shady allowed me to put all kinds of echoes and see everything that was going on. It actually was really nice. Shaders are really hard to test as well. I've never seen a GLSL unit test, but with NIM, you can just write unit tests for your shaders. It's pretty neat because you just run them in the CPU mode at the time of the test. Another problem with GLSL shaders is you can't share them with the rest of the code. You've written a cool math routine and you want it to be available for both shader and the CPU, and now you can't because they're in different languages, right? But now that problem doesn't exist. Another cool thing that I found is there's no need to context switch. When I was switching from writing shaders to writing NIM code, I would constantly put on semicolons. I'll put the variable declaration in the wrong place, but that's gone. I can just use normal NIM now. It's like much easier to write the shader code. Shady is just a very large macro. 2GLSL just takes a NIM node. That's what macros take. And then it goes and it's like, what kind of NIM node you are? There's all kinds. There's like an assignment. There's an influx, which is plus or minus. And there's a call. Is it a dot expression? Is it a bracket expression? Like, I just look at the NIM node and then I generate the appropriate GLSL translation. It takes a lot of work, but each little bit isn't that complex. And this is what the output of that flare function that we saw. You see, it outputs it as main, because that's like the main, that is what was a requirement by a GLSL. And then you can see we have a vector, C equals, a vector, and then a bunch of math code. It's the exact same code as in the NIM version, just slightly translated. And it actually doesn't look that bad. I highly recommend this method of writing shaders. It has saved me so much time. Shady allows you to write compute shaders as well. Compute shaders are really fast and super cool, right? For some workloads, the compute shaders just blow the CPU out of the waters. Of course, not all workloads are good for the GPU. For instance, if you're doing lots of allocations or like tree walking, it's not as good. But if you just have a bunch of data in sequential format and you want to crunch through it, it's amazing, right? Another cool thing about writing your compute shaders in Shady is that you can just, if for instance, you're running on Mac hardware where the OpenGL compute shaders are not supported, you can just choose to run them in the CPU mode. Yep, it is slower, but it does run. So, I don't know, it's pretty cool. Another one of my libraries I want to talk about is Genny. Genny generates a shared library and bindings for many languages, sort of like Swig, but for Nim. Please visit it at treeform/Genny on GitHub. The general idea behind Genny is that I believe Nim can get a wider adoption if it's easy to use with other languages. I want these Nim libraries to infiltrate themselves into code bases of larger teams that use many languages and then slowly grow there over time. If a team uses Nim for a small thing, they can go, hey, we already use Nim, let's use Nim for something else. And I think that's a good way for Nim to infiltrate, big companies, startups, and other teams. Before looking at Genny some more, I also want to introduce Pixie. Pixie is our to-do graphics library. It's written in Nim. It is similar to Cairo or Skia. It can do all kinds of vector graphics, which is really cool. You can find it at GitHub, Treeform Pixie. I originally started Pixie as a way to learn how Cairo or Skia work, and I've ended up writing a full-fledged library. I think Pixie library is pretty cool. I want other people to use it. I want people to use it from C, or use it from Python, or use it from Node.js, or use it from Ruby. I want my Pixie to be available in a bunch of places. How to do that? What do I need to do to make this possible? I think a high quality bindings as a shared library is the way to do this. Genny's goal is to generate the best possible binding for the target language that we support. What do we need to do to achieve that goal? Here's a bunch of Genny ideas. First off, I think the naming convention that the Genny generates should be familiar in the target language. If the language uses camel case like Nim does, the name should be relatively unchanged. If the language uses snake case, for instance, like Python or C, then yeah, we should rename everything to snake case as we export that. If the language just uses something weird like kebab case, mostly Lisp languages, it should convert to that. It should feel natural in the language where it is used. Some more of Genny's ideas is that make the exportable objects behave like object-oriented objects with members, method, and constructors. Many of the popular languages are object-oriented. While Nim isn't particularly object-oriented, it does the uniform call syntax, but it should behave if we export it to another language just like another object. It should just feel natural in that language. Another things that would make it feel natural if we pass optional arguments as well as enums and other constants. Like if that just works normally, how it usually works in the language, I think that would be great. Some other ideas is to generate helper methods like equality or as no checks, overload math operators, plus, minus, multiplication, divisions, all that should be handled if the language support it. For example, C doesn't support these operations while Python does, JavaScript doesn't while Ruby does. Those kind of things need to be tailored for the language. Another thing is I want to export sequences just like normal sequences like you would use in a language with the bracket syntax. It needs to feel natural to a native array. It is possible, for instance, to do that in Python and Ruby, and less so in C and JavaScript. But yeah, you have to meet where the language is, kind of make it nice to use. Basically make it so you don't even feel like you are not using the native language. Some other more complicated thing is that we need to synchronize the bindings between the language garbage collector and Nim's arc garbage collector. So for example, if you have an object in JavaScript that holds a reference to one of Nim's objects, if that object gets delocated by the GC, it needs to also delocate Nim's object as well, transparently. That needs to work. And we even do some nice things like we copy the comments to the binding so that other tools can use them, like the editors or the IDEs. They can just show the comments as well as doc generators, etc. Again, the library must feel natural in that language. So what does Genny look like? How would you use Genny to expose Pixie? Here's how. You would import both Genny and Pixie in your bindings, and you would go and you would use a macro. Export constants, right? And we take a bunch of constants from Pixie, like default miter limit or auto line height. Those constants just exist in Pixie, but now we'll export them through Genny, right? Those constants don't exist in the shared library. They exist in kind of like a header file for each language. Then we have other things to export like enums. Enums don't behave the same in different languages. Like C prefers enums as constants. Other languages do different things. So when we export the enums, they just feel natural in that language. Then we have another macro that exports procs. Again, you just export that proc. You do read image is one of our pixie procs, read mask, another pixie proc, read typeface, right? You just like stick them in there, and then Genny will figure out how to export them correctly for the target language. Next, we have another section called export object, which is export simple, non-ref, allocated on the stack object. So here we have a matrix 3. It has a constructor. A bunch of languages have a special place for the constructor. Nim doesn't really, but a bunch of languages do, so we have to honor that. We mark a constructor. Then we have a bunch of procedures. Here we have a multiply, matrix by matrix. This will actually get turned to a multiplication symbol. If the language support that, it'll be operator overloaded. For instance, in Python, it'll be multiplication. In Ruby as well, but in languages like C or JavaScript, no, it'll be a mul function that you call on the matrix, just like it is natural in that language to use. And then finally, for the most complicated macro, we have export ref object that exports an image. It exports it by a reference, so not on the stack. So a bunch of access like field access requires special handling. But again, we try to make it feel very natural. If you create an image in Python, you can just do .width.height on it. But in Nim, it gets translated to calling the thing and then going through like this bridge and then returning the width back. It's really cool. Again, we mark a constructor. Here's something interesting. We're actually marking a specific constructor that takes an integer and an integer. Part of our macros kind of scan that type information and find the correct function. Then we export all the procedures that will get attached onto the image. So we have the right file. As you know, Nim has the right file where you write the string data to the string file name. We also have our own write file that writes images, but you want to attach that to the image objects in whatever language we are working with. The same thing with copy. Pixie has many copy methods, but here's the one specifically for the image. And then we get a couple regular methods, get color, set color. Here's an example how you would draw a heart in Nim using Pixie. You have an image fill, and then you have the SVG path, then you parse the correct color, and then you send it in, and that's how you would fill that using Nim. Here's how you would draw a heart in Pixie Python. This is our Python bindings to Pixie. There's several different things here. First off, Python prefers module names to be present. So we have Pixie, the module name, dot. Then we have the parse path, which is the, it is different from Nim because Nim was in camel case, but this is a snake case. We've kind of translated the path name to something that looks like, that looks normal in Python. Right? Then we have pixie.paint, which uses a constructor. Then it uses a constant pixie pk solid color. Then we have then we set the color again using the normal Python stuff, and then we fill image using the fill image path with our path and paint. Simple. Here's how you draw a heart in Pixie C. So here you can see that we have C requires a lot more typing. So we create a path. In C, it doesn't really have namespaces, so we're using function prefixes like it's very normal to do in C. So we have Pixie parse path again in snake case. Then we have we create a paint. Again, because C doesn't have constructors, but we have a function Pixie new paint. It's very normal to do that in C. Then we have Pixie paint set color, again with a parse color. Then we have Pixie image fill path, very similar to the other ones we saw, except in this one takes a bunch of extra parameters. Why? Because C doesn't have optional parameters, so we have to specify them. So we have to specify a default matrix and the winding order. Again, Genny is just a set of large macros. What do those macros do? They walk the Nim AST node once. It actually walks it once as untyped in order to produce that nice language. It creates a typed version, and then it walks them again after typing with another macro, so we get the types back. It gathers functions, it types and constants and enums, like it just gathers all that, and then it generates the Nim glue code as well, because remember, you have to have a little bit of glue code to access Nim, and then it generates the kind of glue code on the other side in the language that it's for. Here's an example of what Genny output. What does it give you? It gives you a Pixie DLL for Windows, then it gives you a Pixie SO for Linux, and then Pixie dilib for Mac. right? And then you have the individual binding files. So we give you the PXY, which actually uses C types to access the DLL. And then we give you the PXH, which is needed for C to bind to those DLL. And then we also give you PXJS, which uses the foreign function interface to connect to that. And then we give you PXRB, which is the Ruby version of foreign function interface again. And so you can use PXY in all these languages. Imagine trying to maintain all these bindings manually without Genny. This task is very repetitive and error-prone and extremely boring. The bindings would need to be kept in sync and they need to stay up to date. It's like a lot of busy work that no one wants to do. This is exactly where the power of the macro comes in. You can create amazing things with macros, and Genny is just one of those examples. Again, I want to remind you about the metaprogramming power levels. You have generics on the kind of least powerful, and then we have templates and macros. Remember, they're really cool. They have each of their uses, and use the most minimal power that you need for your project. And don't go overboard. Make sure the macros and the templates actually save you space and complexity rather than just introduce just another thing for someone to understand. Hopefully during this talk I've answered the question, why should you use metaprogramming? Through real-world examples. Give you an example how I use metaprogramming in VMath, in Jsony, in Shady, and in Genny, how the power levels work. Thank you for listening to my talk. If you have any questions, please feel free to post them in chat or contact me directly through email or on my GitHub. Thank you very much.